5-4, dividing polynomials. So our objective for this section is to divide polynomials two ways, using long division and then using synthetic division. Our essential understanding is that you can divide polynomials using steps that are similar to the long division steps that you would use to divide whole numbers. For instance, here is what we used to do way back in the day when we did long division. So let's take a look at this real quick to remember how long division actually worked, and then we can take those same ideas and bring them over into polynomial long division. So first, remembering back to, second grade, third grade, whenever you did long division, we would ask ourselves, is 1 divisible by 5? No. So we would take these first two terms, 12, and we would divide them by, we would say, how many times does 12 go into 5? Well, the answer is 2. But I would always put the 2 over the second term, not the first term, the second term. Then the next step would be to multiply and then subtract. Then we would repeat the process, bringing down the 8. Okay. So then I would say, how many times does 5 go into 28? Well, it goes in 5 times. Multiply 5 times the 5 gave me a 25, and then I would be left over with 3. Now, with whole numbers, we would then maybe put some decimal points and see if we could get this to work out with a couple decimal points. But what we're going to do now is we're just going to use a remainder. Okay? So now you could write a remainder like that, remainder 3, but we're going to use fractional remainders. So 3 divided by my quotient of, or my divisor of 5. So my answer to this particular problem was 25 and 3/5. And then we can, of course, look at a couple other long division problems, making sure that we actually understand the algorithm that we actually would use to divide these. With this last one, changing this last answer to 17 and 19/31, not remainder 19. Now, with this in mind, we could then look at how we can divide polynomials. Okay? So when you try to factor a polynomial, you are trying to find a divisor of the polynomial that gives you a quotient, the other factor, and a remainder of 0. This suggests that being able to divide one polynomial by another can help you factor. And that's where we're going in the next section, in section 5, is we will try to figure out, with guessing and logic and quick division, the factors of a polynomial using division. So here is what polynomial long division looks like. Compare it to regular long division. Okay, we still have my same sort of stuff going on here. Okay, so I'm dividing this polynomial by 2x plus 1. I start by looking at this first term and seeing how many times does 2x go into 6x squared. Well, it goes in 3x times, because 2x times 3x is 6x squared. So then I take this 3x and I multiply it by both of those terms. That will give me this term right there. And then I subtract. Get my answer, bring down the next term, and keep going. Same sort of idea that we do in regular long division, we do in synthetic long division. So let's try one. We are going to take x plus 5, and we're going to divide it into 4x squared plus 23x minus 16. Okay? So my first step is, how many times does x go into 4x squared? Well, it goes in 4x times, right? If I take 4x and multiply it by x, I would get 4x squared. So my first term is going to be 4x. But just like polynomial division, I don't want to put it over the 4x squared. I want to put it over its like term. So I want to put it over the 2x to the third power. Okay. Now I am going to multiply this 4x by both of these to get my term to put underneath. Okay, so that would be 4x times x gives me my 4x squared. 4x times 5 gives me a 20x. And now, for my last term, I want to subtract. So that's going to change this sign and that sign. So 4x minus 4x squared gives me 0. And that was the point. That's what I want. I want that first term to cancel out so that way I can move this problem forward. All right. Next, we would have 23 minus 20. That's going to be 3x. And then bring down my next term. Okay. Now I want to repeat the process of dividing, multiplying, and subtracting. So how many times does x go into 3x? 3. Multiply. 3 times x gives me 3x. 3 times 5 gives me a positive 15. And subtract to give me a negative 31. Now, when the degree of what's left over at the bottom here is less than the degree of what you're dividing by, you are done. It's not possible to divide x into 31 anymore. So that means this particular problem, we have a remainder. So my quotient is going to be 4x plus 3. My remainder is going to be 31. The way I want you to write the remainder, however, is not like this. Okay, we're going to do the same thing that we did with the original problem, is we're going to write it as a fraction. And because this is a negative, I can put a minus 31 over your divisor, whatever it is you're dividing by, x plus 5. Okay. Let's look at one more. Same thing. Okay, so we're going to use polynomial long division to divide 3x squared minus 29x plus 56 by x minus 7. And then I use 3x squared minus 29x plus 56. And divide first. Divide x by 3x squared. What do we get? We get 3x. 3x times x gives me my 3x squared. 3x times minus 7 gives me my negative 21x. Now, we subtract, which in order to do that, I change the sign of everything in my little depressed polynomial right there. So now I get 0 and I get a negative 8x and bring down the 56. Next, we take x, divide by 8x, we get a negative 8. Multiply, we get a negative 8x plus 56. When I subtract these, I get a remainder of 0, which means that my quotient is 3x minus 8, and my remainder is 0. Okay, so the division algorithm for polynomials follows the same pattern as long division for real numbers, right? We could divide a polynomial p of x by a polynomial d of x to get a polynomial quotient q of x and a remainder of r of x. So that's what we're doing here. We're taking my original, we're dividing it by something called the divisor, and we're getting a quotient and a remainder. Okay? So the result is, in order to get my original polynomial, I could multiply the divisor and the quotient together and then add in the remainder. And that would give me my original polynomial back. So for instance, if I wanted to get this polynomial back again, I could multiply x plus 5 times 4x plus 3 and then subtract off 31, and that would give me my original polynomial. Okay. If my remainder is 0, then the original polynomial equals the divisor times the quotient, and that they are factors. So that means in this problem right here, if I wanted to get my original polynomial back again, all I would have to do is take these two and multiply them together, and that would give me my original polynomial because the remainder is 0. Also, x minus 7 and 3x minus 8 are both factors of 3x squared minus 29x plus 56. So that's what that's saying down at the bottom there. To use long division, p of x and d of x should be in standard form. with 0 coefficients where appropriate. This is very important, okay? You need to include 0 coefficients as placeholders if they are not there. The process of long division stops when the degree of the remainder r is less than the degree of the divisor. So what do we mean by this? What do we mean by 0 coefficients? If we have a problem that looks like this, I must notice that my divisor is missing an x term, and my original polynomial is also missing an x term. So when I'm going to use long division here, I must include them plus 0x plus 1. I have to include them both places. 3x to the fourth minus 4x to the third plus 12x squared plus 0x plus 5. So I had to include a 0x in both my divisor and my original polynomial. Okay, I have to include both the 0x terms. Okay. Now I'm going to keep dividing this until the degree of my remainder is less than 2. As soon as my degree of my remainder is less than 2, I'm done, because then x squared wouldn't go into that anymore. So my first step is to take 3x to the fourth, divide it by x squared. See how many times it goes in? It goes in 3x squared times. So multiply, and I'm going to multiply the 3x squared by all 3 terms to get 3 terms down here. Okay. So let's 3x squared times x squared gives me 3x to the fourth. 3x squared times 0x gives me a 0x to the third. That's okay. It's okay to get 0 terms. They're just there as placeholders for the other terms. 3x squared times 1 gives me a 3x squared. Remember to subtract everything. Doesn't matter for the 0. Okay, so that cancels. We have a negative 4x to the third, and we have a plus 9x squared. Okay. And then bring down my 0x term. Okay. Next, divide x squared by 4x to the third, or think, how many times does x squared go into 4x to the third? That would be a negative 4x times. That gives me a negative 4x to the third. That gives me a 0x, which is still okay. And negative 4x times negative times a positive 1 gives me minus 4x. I'm going to subtract these. So I'm going to change the sign of everything, which gives me a 9x squared and a 4x and a 5. Bringing down my 5. Okay. And making a 4 that looks nicer. Okay, last step is we are going to divide x squared by 9x squared, and we're going to get 9. Multiply the 9 across gives me 9x squared plus 0x plus 9, and subtracting gives me 4x minus 4. Now, the degree of my remainder is 1. The degree of my divisor is x squared, which means the degree of the remainder is less than the degree of my divisor, which means we are done. So 4x minus 4 is actually my remainder. So I can tack that on at the end as a fraction over, and I don't need to put a 0x as part of my answer, right? I can leave that out now. So x squared plus 1. So this particular question was asking if x squared plus 1 is a factor of 3x to the fourth minus 4, blah, blah, blah. The answer is no. The answer is no because I have a remainder. And then, of course, if I wanted to get back to my original equation, I could take my divisor times my quotient, add in 4x minus 4, and that would give me my original equation again. For a question like this, is x minus 2 a factor of that? If it is, write it as the product of two factors. Okay? Even though this looks simple, okay, this question gets a little more complicated because okay, we need to include all the missing zeros. That's x to the fifth plus 0x to the fourth plus 0x to the third plus 0x squared plus 0x minus 32. So even though this problem has a binomial and a binomial, okay, when we write it out, when we include all the missing zeros, right, it turns into a pretty large problem. Okay, so let's do it. Divide x to the fifth by x, we get x to the fourth. Multiply x to the fifth minus 2x to the fourth. Subtract gives me 2x to the fourth. Bring down the 0. Okay. And do it again. And as you notice, or as we go forward, you're going to see that we're going to get all sort of factors of 2. So divide x by 2x to the 4, we get 2x to the third. Multiply 2x to the fourth minus 4x to the third. Subtract. Bring down the 0. Okay. Then do it over again. Okay. How many times does x go into 4x to the third? It goes in 4x squared times. So we need 4x to the third down here minus 8x squared. Subtract them. We get 8x squared. Bring down the 0x. So now we're going to put up a plus 8x. And this gives me 8x squared minus a 16x. Subtracting gives me 16x. Bring down the minus 32. And now, when we put a 16 there, we're going to get 16x minus 32, which when I subtract those, gives me a remainder of 0, which means that x minus 2 is a factor of x to the fifth minus 32. So I can write p of x, so I can write this polynomial as the product of two factors. So my new polynomial is going to be equal to x minus 2 times my quotient, this thing right here. So that's going to be x to the fourth plus 2x to the third plus 4x to the squared plus 8x plus 16. And if I were to multiply those two polynomials together, I would get x to the fifth minus 32. Okay? Now, there is an easier way to do this for some problems. And it's up to you to realize when we can use this simplified method and when we can't. It's called synthetic division. Okay, so synthetic division simplifies the long division process for dividing by linear expressions. So that's the first thing. In order for synthetic division to work, you must have a linear expression. This is not a linear expression. It's a quadratic. So you need x plus or minus a letter. Okay? The other time that you really shouldn't use synthetic division is when we have some sort of number in the front here, and I'll show you that later. But for now, as long as we have a linear expression, we can use synthetic division. To use synthetic division, write the coefficients, including any missing zeros of the polynomial, in standard form. Leave out the variables, leave out the exponents. Okay, so all you're going to write is the number in front. For the divisor, reverse the sign. So we're going to use the roots. So for instance, if we had x plus 2, my divisor would be negative 2. Right? We would use the opposite. Right? This lets us to add through the problem instead of subtracting, which makes it a little bit easier. So let's take a look at this. So divide that polynomial, x to the third minus 14x squared plus 51x minus 54 by x plus 2. Okay, so first, we're going to look at this divisor. We're going to see, is that a linear factor? It is. So we're going to start with putting a in a little box off to the side. Okay? A is going to be -2. We're going to use the opposite, and we're going to put it in this little separator. Okay? Then we're going to take a look at my polynomial, and we are going to take only the coefficients. 1, -14, 51, and -54. Going to put a line, and now we have our problem set up. Okay, so step 1 was to use my root, not my factor, my root. So reverse the sign. So instead of +2, we use -2. That goes there. Okay. Step 2, set up my problem with only the coefficients. Okay. Now let's get started. Bring down, the first step, once we have this set up, the first step is to bring down this 1 to the bottom. Okay. The next step is to multiply the coefficient by the divisor. Okay. So we're going to take this 1 and we're going to multiply it by -2, which is going to give me a -2. And it goes sort of one level over. So we multiply, and then I put my answer up and to the right. And then with these two, I add them together to give me -16. And then I do the process over again. Okay? So the answer that I put right there is going to be a -16 times a -2, which is going to be a positive 32. And then going down, I add those two together to give me an 83. Multiply the 83 by the -2 to give me a -166. Add these two together to give me a -220. And then the last number is your remainder. So my quotient then is this polynomial right here. But you have to translate it into an actual polynomial. So we are dividing x to the third by something with an x in it, which means that my degree is going to go down by 1. So instead of starting with x to the third, I'm going to start with x squared, and I use these three numbers as my coefficients. So I have x squared minus 16x plus 83, and then I just put my remainder, which is going to be a minus 220 over whatever it is I was dividing by. Not -2, I'm dividing by x plus 2. And there is my my new polynomial. My quotient would be x squared plus minus 16x plus 83. My remainder would be -220. Let's look at another one. Okay. So I'm going to divide by x minus 7, which means that I put a positive 7 in this little box over on the left. Put the coefficients. 1. There is no x squared. If you look at this problem, there is no x squared, which means you need to put a 0 for x squared. Minus 57 plus 56. Put a line, and now I'm ready to start. So the hardest part about this is to realize that any missing coefficients, you need to put a 0. Okay? So bring down the 1. Multiply. Add. Multiply. Add gives me a -8. Multiply gives me a positive 56, which leaves me with a remainder of 0. And I usually draw that little line to separate the remainder so I can see it clearly. And now I actually have my new polynomial as x squared plus 7x minus 8. Okay? And if I wanted to, I could factor that into x plus x minus 8 x plus 1, both of those times x minus 7, because that's what I divided by, and my original polynomial is now actually factored. Okay. So, even though that's not really what the question asks, but that's kind of where we're going. What's the quotient in the remainder? The quotient would be x squared plus 7x minus 8. The remainder would be 0. Okay, let's take a look at a word problem. Okay, so let's use synthetic division to help us solve this word problem right here. The polynomial x to the third plus 7x minus 38 minus 240 expresses the volume in cubic inches of the shadow box shown. What are the dimensions of the box? Well, I know that one of the dimensions is x plus 5, so I could divide that out and then have something that I could factor. So let's do that. So x plus 5, I'm going to put a negative 5 in my little box here, and then I'm going to put my coefficients, 1, 7, minus 38, minus 240. Bring down the 1, gives me negative 5. That's a 2. That's a negative 10. That's a negative 48. Negative 5 times negative 48 is a positive 240. And I expected this to work out because it was actually a factor. It's shown to me as a factor. The point of this was now I have this simplified where I have x squared plus 2x minus 48. And if I wanted to, I could factor that into x minus 6, x plus 8, which means that together with this factor, that's the length, the width, and the height. In the hint, it says the length is greater than the height or depth. Well, the biggest one of those, no matter what x is going to be x minus 8. So the length is x plus 8. X plus 8 is going to be the height, and then minus, whoops, this should be a plus, right? Because that's a plus right there, not taking the sign there. So we have my other two as the length and the width and the depth. Okay, so let's try something with the remainder theorem. Okay, the remainder theorem provides a quick way to find the remainder of a polynomial in a long division problem. So the remainder theorem says that if you divide a polynomial p of x of degree n is greater than 1 by the factor x minus a, the remainder is p of a. That means if you plugged a number into the function, you would actually get the remainder that the factor x minus a would give you. But then the opposite is also true. It means that if you wanted to find the value of a function at a particular number, the answer would be the remainder if you divided that factor by it. So to figure this out, to use the remainder theorem here, I could plug in 3 to this function. I could go 3 to the 5th power minus 2 times 3 to the 3rd power minus x squared, minus 3 squared plus 2. I could do that. Okay, and there's nothing wrong with that. But there's a faster and easier way to evaluate this particular polynomial at this number. Okay, we can use the remainder theorem. I know that if we were to divide this polynomial by x minus 3, that the remainder would be what this function equals at 3. So I can take my number 3, plug it into a little synthetic division problem. 1, I need x to the 4th, so I put a 0. Minus 2, minus 1, I need x, so I put another 0, and 2. And if I evaluated this, it could work, it could not work, but my answer is whatever I get as a remainder. So bring down the 1, multiply, add, multiply, add, multiply, add, multiply, times 3 gives me 60, add, and multiply, and add one last time to get 182. 182 is my answer. That is what P of 3 is equal to. So if I were to work all this out, I would get an answer of 182. Slightly easier to work through a synthetic division problem than it is to figure out what 3 to the 5th is, unless you happen to have a calculator. But there's also a lot of places to make mistakes with the signs, especially if you have a negative that you're trying to square or do something like that. So definitely is easier. Okay. Let's try it again with a -4. Okay. 1, -3, minus 28. We need a squared term, 5 and a 20. Okay. Bring down the 1, multiply, add together. We get a -7. That's going to be a positive 28. 0, 0. Add them together, you get 0. Multiply, you still get 0. Add them together, you get a 5. And now we get a -20 and a 0 as a remainder. So P of 4 is equal to 0, which means that x plus 4, that this term right there, this factor, or sorry, that factor is actually a factor of that polynomial. And that's where we're going in the next couple sections, is we're going to try to use this method, use synthetic division, try to get 0 as a remainder, which would tell me that this is actually a factor of my expression. Now, synthetic division works great and is easy until you get problems. We didn't really talk about this too much. Until you get a problem that looks like this. Okay? So that's still a linear factor. So if you wanted to, you could still use synthetic division. Okay? But here's the problem. Okay, let's rewrite. Let's do this over. Okay? Here's the problem. I need it to be x plus or minus something. Well, I could divide both of these by 3, and now I would have x plus 2/3. Okay, so in my little box over here would be a fraction. That, number one, makes it more difficult. Number two, not only do I have to divide the factor by 3, but I also have to divide the entire polynomial by 3. So that would turn this into 1/3, -14/3, 51/3, and -54/3. Okay? Which definitely makes the problem a little bit more complicated. So you always can use synthetic division if you have a linear factor like that. You could try if you have a linear factor that looks like this. You never can use it if you don't have a linear factor, if you have something that is x squared, x to the third, x to the fourth. Okay. But be aware that synthetic division is faster, more efficient, and we will be using it a lot in order to try to guess factors of polynomials. And that is 5-4, dividing polynomials.